Okay, Assalamualaikum warahmatullahi wabarakatuh and good afternoon everyone. So my name is Zainul. So you see me again with this DLS session. Organized DLS stands for Distinguished Lecture Series, organized by the Faculty of Engineering, University of Malaysia, Johor Bahru. So today I'm Zainul from the School of Chemical and Energy Engineering, one of the schools under the Faculty of Engineering UTM. So today we're going to have our next DLS series, which we are very grateful to have our speaker this afternoon all the way from Sweden, Professor Ulrika Rova. She's a professor in biochemical engineering in Luleå University of Technology. We started to get to know each other when we were invited to various conferences. Normally, the one that was held in India, because that was under this particular conferences where people with a specialization or interest in the area of bioresources, biochemical processing, uh, biodegradation, microbiotechnology would gather every year and share our what we have come up in our own research group and research area. Yeah. So as of today, we still looking forward to have um, uh, visible collaboration with Professor Ulrika, maybe in the form of joint publications. Yeah, maybe we can write chapters together, and with that we can follow up with some other research together. Yeah, and with this also, I'm happy to share that in UTM, the Faculty of Engineering is consists of 6 schools. The school where I'm in is called School of Chemical and Energy Engineering. We also have School of Electrical Engineering. We have a School of Mechanical Engineering, School of Civil Engineering, School of Biomedical and Health Sciences, and also School of Computing. So these are the schools, the 6 schools that were previously known as separate faculty. Okay, then after our synergy in 2018, we are now become schools under one Faculty of Engineering. So with that introduction, may I invite our distinguished Dean, Professor Rafiq, to introduce our speaker today. Over to you, Prof.
Thank you very much, Zainul, for chairing the session. Assalamu alaikum warahmatullahi wabarakatuh. Welcome to our 46th UTM Engineering Distinguished Lecture Series. My name is Muhammad Rafiq, and I am the Dean of Engineering, University Technology, Malaysia. Today, it is my utmost pleasure to welcome Professor Ulrika Rova from Luleå University of Technology, Sweden. A bit about our distinguished speaker today. Ulrika Rova is professor in biochemical process engineering at Luleå University of Technology, Sweden. Prof. Rova's research is focused on biomass pretreatment, fractionation, design and use of enzymes and microorganisms for production of fuels, chemicals, and materials from lignocellulose materials. Ulrika has been the national representative in the FBI 1306 Cost Action Valorization of Lignocellulosic Biomass Side Streams for Sustainable Production of Chemicals, Materials, and Fuels using low environmental impact technologies, where she has also been the leader for the working group pre-treatment fractionation of lignocellulosic biomass. She currently heads several projects on different approaches for lignocellulose valorization. So that is a brief biography of our distinguished speaker today. Here now is Professor Ulrika Rova from Luleå University of Technology, Sweden, to talk about the valorization of forest biomass approaches towards a diversified product spectrum. Professor Ulrika Rova, over to you.
Thank you very much. Thanks for the invitation, and also thanks for the nice introduction. This is something really new for me. I haven't done this kind of lecture before, but I think it's a good way to initiate collaboration while it's not possible to travel and meet during conferences. So I will give you some examples of research project that we are doing here at the Luleå University of Technology. And now I hope you will see the full screen of my presentation. Is that correct?
Yes, you can proceed. Thank you.
Very good. So some quick facts about the Luleå University of Technology. So we are located in Sweden, just below the Arctic Circle. So we are actually in the Arctic region. The university was founded in 1971, and we have 69 research subjects within natural science, engineering and technology, economics, health science, humanity, arts, and educational science. So around 57% of the university is focused on research and 43% on education. And we have quite a good external funded research. So about 62% of the turnover actually comes from the involvement of industry. So below you see a fly photo of our campus area. So the research group that I belong to is called Biochemical Process Engineering, and we have two different focus areas. So the first one is the biomass route, where we use lignocellulose biomass and do cellulose, hemicellulose, and lignin valorization. And we also do work on bark valorization, biogas production, and the use of microalgae for valorization of lignocellulose and food waste. And then we work on the more classic biocatalysis research focused on fuel production and also functionalization for chemical production. So this is the part that I will talk about today. But then we also have another track which focus more on CO2 as a carbon source. So we do microbial electrosynthesis, and we also work with the use of enzyme for CO2 capture and conversion. So at the subject, we are 2 professors, 2 guest professors, 2 technicians, 3 lectures, and 4 postdocs and 5 PhD students, and between 8 and 10 exchange students, depending on what kind of program that we have up and running. And we have quite good publication records. So during the last 8 years, we had 240 research publications. And we get funding from the Swedish Research Council, from Formas, Vinnova, and the Swedish Energy Agency. And also we are now part of 4 different Horizon 2020 projects. So why lignocellulose? First of all, we are in a perfect location because Sweden is a forest nation. Almost 70% of our land is covered by forest, and that equalizes to around 28 million hectares of forest. And of those areas, around 80% is actually used. And today we have a higher growth than harvesting. And during the last 90 years, the forest supply has doubled. And this is because the forest is really carefully managed. And we have a lot of national laws that protect the forest and put rules how it should be harvested, how it should be maintained, and also in respect of some environmental concern. And Sweden is the world's 3rd largest exporter of pulp, paper, and sawn timber. And as that you can understand, the export value is quite high. And from an environmental part, the forest is also an important source for CO2 sequestering. And we think that the forest is very important as a source if we want to replace fossil-based resources and go more towards a bioeconomy. But then there are some issues that we need to work on. So first of all, we need to strengthen the competitiveness of the existing process and products within the forest industry. And we need to develop energy efficient technologies that can convert the forest biomass into biofuels, chemicals, and materials in order to replace the fossil-based routes. And we need to find a more efficient use of the raw material, and that includes the forest residues such as sawdust, bark, paper mill sludge, and so on. So that means that if we want to have a circular economy, we also need to think circular chemistry. And one of the most important issues as we see it is that we need to develop methods that enable us to fractionate the three main lignocellulose components. And of course, we need to strengthen the collaboration between all actors and so on. But if we look at the fractionation part, this has not been a focus. Rather, it has been that the pre-treatment method that we use for lignocellulose is focused on a pre-treatment method that is designed to improve the access of polysaccharides. So there has been a focus on the glucose part of the biomass, and fractionation has not been a goal. But it is important to develop both a combined pre-treatment and fractionation technology that enable us to have a process where we can have selective separation of each component, and that we can have a pre-treatment method that gives us easy access to all those components, and that we can recover them in high yields. So to pursue this track, we have during the last 6 years developed a pre-treatment method that we called organosol pre-treatment. And we have combined a solvent process that enable us to solubilize hemicellulose and lignin, and at the same time receive a soluble cellulose fraction that is also defibrated and hence accessible for enzyme hydrolysis. So in this method, we use solvents like methanol, ethanol, or acetone. We have mainly been focused on using ethanol because it's also compatible with if we want to go to production of food components. And the process temperature that we are using is in the span of 185 to 210. And by pursuing this kind of pre-treatment method, we are able to receive a solid cellulose fraction that we can hydrolyze and use the glucose, or we can also, we can at the same time also get a solid lignin fraction that we can use, and we can also separate the hemicellulose that can also be hydrolyzed to their respectively monosaccharides. So here you see a photo of our reactor that is standing in our lab, and we are now upgrading it to a semi-continuous operation. And this is just an example. If we look at the composition of the solid fraction that we get from the organosol pre-treatment. So this example is for Birch, and we can see that we can get up to 86% delignification. And that is very important if you want to work on the cellulose, because if you want to do hydrolysis, it's very important that you don't have any lignin that is attached to the cellulose. So we mainly work with Birch and Spruce. And Spruce, if we do the organosol pretreatment, we can achieve up to 79% of the lignification. So today I will mainly talk about cellulose valorization and some example of how we can use the lignin, because that's very important also. So this is the composition of the lignin fraction that we can achieve after our organosol pre-treatment. And you can see that we have very low impurities in form of ash, and the cellulose content and the hemicellulose content is very low in our lignin fraction. And the same is for Birch, a little bit higher in the impurities. So based on this pre-treatment and fractionation method, we have tried to work in what we call cycles. So we have one cycle that we call the energy cycle, and this is on the topic to be able to actually use as much as the raw material as possible. So we we are not only focused on one of the fractions, but try to find different approaches how to use the others. So for the energy, we have bioethanol, biobutanol, biogas production, and we also use lignin for the production of biodiesel that is suitable for the marine sector, and it can also be used for the production of biojet. And for the material part, we use both cellulose, lignin, and hemicellulose for the production of biochar, carbon fibers, biocomposites. And today I will give you some examples on the production of nanoparticles and their use as flotation collectors in the mining industry. The first topic I will talk about is the production of nutraceuticals that we do from the cellulose fraction. So we work both on prebiotics and also on polyunsaturated fatty acids. So during the last years, there has been a rather large focus on the human microbiota, as it has been shown that a healthy consortium can actually promote health and has an impact on diseases. So there has been a focus on probiotics, but now a prebiotic is also gaining a high interest. And prebiotics is non-digestible food ingredients that is not degraded by our enzymes, but they are used and fermented by intestinal microbiota. So they can actually promote the growth of healthy bacteria. And it has been shown that it's very important when it comes to type 2 diabetes, obesity, allergy, cancer, and so on. So there is a growing interest. And non-digestible oligosaccharides, they are an example of a prebiotic. So prebiotic, they are actually food for the probiotics. And NDOs, they are carbohydrates with a low degree of polymerization. And it has been shown that it can promote the growth of bifidobacteria and lactobacillus, which are the most common probiotics. So there are already a number of different types of NDOs on the market, and they are either extracted from natural sources, or they can be obtained by enzyme processing or produced chemically. So we have focused on the use of cellubiose as a functional food ingredient and to be a prebiotic. So they can, like a normal prebiotic, they are resistant to digestion, and they have been shown to have a high prebiotic potential. And what is good with cellubiose is that it's already used today as a sweetener if you want to introduce something as a food supplement. So we are currently working in one project where we are looking at the option of using birch and spruce biomass for the production of prebiotics. So we start with conducting this organosol pre-treatment and fractionation, and then we focus on the cellulose fraction. And this is just a summary of the composition analysis, what we can get from using birch or spruce. And here on the right, you see the scheme for the project. So it includes developing efficient pre-treatment methods, and then doing enzymatic hydrolysis, work on product recovery, and then finally evaluate the potential of those costs to be used as a prebiotic. So one very important step when you have received the cellulose is actually to do the enzymatic depolymerization, because we need to decompose the cellulose into cellubiose. Cellubiose consists of 2 glucose units. And the problem is that when you use the commercial available enzyme cocktails, they are designed to actually process the biomass to complete degradation into glucose. And we don't want to glucose, so we want to stay at cellubiose. So we have used 2 different approaches. One is where we have designed our own enzymatic cocktails. using in-house produced enzymes. And the other strategy has been to use already commercial available enzyme cocktails and to modify their performance. So I will explain that to you. So in the first one, where we actually make our own enzyme cocktails, we start with screening the activity of 14 different enzymes provided by Enzytec. And we checked their activity on regarding the Cellubiose yield. And then we chose one enzyme. It's the pH Cellubiohydrolase 6A. And then we designed some experiments, and from that we could conclude that the optimal enzyme combination for receiving a maximum of Cellubiose needed the addition of EG5, CBH7, LPMO, and CBH6A as well, and also EG7. And by doing that, we could convert almost 22% of the cellulose if we were using Birch, or almost 20% if we were using Spruce. And those two, and this work is summarized into recent publications. And in the second strategy, we wanted to see if we could modify the activity of already available enzyme cocktails. So what we did was actually to use an inhibitor that could actually inhibit the beta-glucosidase activity and stop Cellubiose to be hydrolyzed to glucose. So we look on the effect of pH, enzyme load, hydrolysis time, and the effect of temperature. So we used to work with an inhibitor called conduritol, and it's a potent irreversible inhibitor of beta-glucosidase. And by looking at assessing the best condition, we could conclude that a concentration of 3.95 millimolar was the best to be used, because that will actually make it possible to receive as much Cellubiose as possible and as little glucose. So based on those two different strategies, we wanted to scale up. So in one study, we used Birch and did the organosol, did the tailor-made enzyme hydrolysis, and ended up with the recovery of 787 milligrams of Cellubiose. And here you can see the ratio of Cellubiose and glucose. So it was 21.1. And then we did exactly the same with the Birch, but here we used the Celluclase, the commercial available enzyme cocktail, and we used the inhibitor. And here we could obtain almost 1 gram of Cellubiose, and the Cellubiose to glucose ratio was very good. So we do also ultrafiltration and nanofiltration to try to optimize the ratio of glucose and Cellubiose. And based on this, we also then wanted to look at the prebiotic potential. So we used the most common probiotic strains, so 3 different lactobacillus strains and 3 different bifidobacteria strains. And then we assessed the growth and production of metabolites when using glucose or commercial available Cellubiose or COS that we had produced from Birch. And then we could see that they had the growth on commercial available Cellubiose was very good for Plantarum and Gaceri. So based on that, we also then tested the cost that we produced from either the first strategy or from the second. And we could see that the promoted growth for Plantarum quite good, but the effect on Spruce was rather low. And we think this is explained because that we have some phenolic residues from the spruce process that is actually negative on the growth promotion of the lactobacillus. And then we also did the impact on growth for using this commercial strategy. And we could see that they all promoted very good the growth. And we have also been working in close collaboration with a company in Sweden, in Umeå, that works on the production of pre and probiotics. And they compared our cost that we produce with the commercial available inulin. And they could see that cost actually had a much higher impact, promoting growth much better than the inulin. So the conclusion from those studies is that we can actually combine an efficient fractionation process where we get a pure cellulose fraction, and that we can perform a controlled enzymatic hydrolysis that enable us to get high yield of cellobios and low yields of glucose. And it has been possible to scale up the process. And finally, the most important part, that we can actually promote the growth of beneficial lactic acid bacterial species. So this work is going to an end next spring, and we have been very happy with the results so far. Another track that we are also looking at is the production of nutraceuticals from forest biomass. So we have two different families of essential fatty acid, the omega-6 and the omega-3. And due to low conversion rate, it is recommended that the EPA and DHA needs to be provided by the diet. And there is a growing interest, or a quite strong market for this kind of polyunsaturated fatty acids. So the most common source for omega-3, for example, is to use fish. But then it comes to a complication, because there is the increased demand will also put a stress on the marine ecosystem. So there are some alternative sources for omega-3. And one is to use vegetable oils from transgenic plant, and the other one is to use oleaginous microorganisms. And some marine microorganisms, such as microalgae and diatoms, they are the primary producer of polyunsaturated fatty acid in the aquatic food chain. So we wanted to explore and to see if we could actually develop a microalgae platform for the production of PUFA from forest biomass. And some microalgae, they can actually grow heterotrophic. That means that they can actually use low-cost renewable substrates. And working with microalgae will also give us tools that we can improve the microbial growth. We can design the nutrient requirement, and we can also control the cultivation conditions. And compared to plants, those are less influenced by the seasonal and climate variation. So the strategy has been then to screen different oleaginous microalgae for high lipid accumulation, and also to select what kind of biomass resources that we can use for the heterotrophic cultivation of the microalgae. So we have been published quite a few studies on this kind of approach. And the first one was where we looked at the possibility to use a marine diatom called the trichornitum, and to use as a carbon source cellulose that we could get from spruce or birch, and then hydrolyze it by enzymes. And then to check if we can actually use that as a source to promote heterotrophic growth, because there has been indication that this can actually induce an increased PUFA production. So this is a summary where we compared the cultivation, phototrophic cultivation versus mixotrophic mode of cultivation using this specific marine microorganism. And we could see that if we look at the yield of EPA, that when we, here is the phototrophic mode of cultivation, and here is when we switch to a mixotrophic mode of cultivation using heterotrophic then. And we could see that actually we can increase, this is using pure glucose, and here's when we use glucose from Birch or glucose from Spruce. So we can see that we could actually enhance, if you compare with the phototrophic mode of cultivation, we got an increased productivity of EPA and also DHA. So this was very promising. And then apart from omega-3, we have also been looking at scoline. Scoline is a polyunsaturated hydrocarbon triterpenoid, and it has some commercial interest because it can be used in the cosmetic industry and also in the pharma industry. And there are also some studies looking at the use of scoline for biojet fuel production. Normally, scoline is obtained from the liver of deep sea sharks and whales. But this is not maybe a very sustainable production method. So instead, we have been looking at using marine microorganisms to heterotropically produce both DHA and scoline. And in this study, we used a marine organism called Aranchytricum and looked at if it was possible for this species to grow on hydrolysate from forest biomass. So first we compare it to the production of lipids when we used the pure glucose as the carbon source, and then we used the hydrolysate that we obtained from organosalt pre-treated birch. So you can see that the lipid content was the same as when using glucose as the carbon source. So then we used the birch hydrolysate and compared the productivity either when we cultivated the species in flask or in a bioreactor. And you can see that we could actually get a much higher DHA concentration when the cultivation was done in more controlled conditions, and the same for scoline. So that was very, very promising. And then using the same species, we also did some kinetics where here you can see the kinetic for the flask cultivation, and below you can see what happens if you change the system to instead use a bioreactor, and we can see that we got much higher lipid content much earlier compared to when the organism was cultivated in flask. And also the fatty acid profile showed us that we had a higher DHA content when we cultivated in the bioreactor. So that was very good for us. And then we also looked at the scoline production, and we could also achieve high concentration of scoline when we changed from flask cultivation to bioreactor cultivation. And this is just a comparison with other published results. And we were actually the first one that could show that we could use forest residues for the production of scoline and DHA. So this is used on pure glucose. And then in a very recent publication, we looked at the possibility to co-produce DHA and scoline using a marine species belonging to the Strastocyotrids. And we looked at the impact of the aeration rate, and we could see that it's very important to control the dissolved oxygen, because if you have higher aeration, you will also produce much more biomass, and you will also get a higher lipid content. And we optimized this process looking at the optimal glucose concentration. So this was using pure glucose. And we could see that a glucose concentration of 6 grams per liter was the most optimal one. And using that one and optimized the condition, we could see that moving into using bioreactors, we were able to get much higher content of DHA when compared to when doing the flask cultivation. And this is mainly due to that during the bioreactor cultivation, you have the possibility to control the oxygen supply. And then we switched to using spruce hydrolysate that was enzymatic treated. And we did flask cultivation and bioreactor cultivation, and we could see again that the cultivation in bioreactor actually enhanced the production of DHA. So this is just a summary showing that the most likely the impact of oxygen has a high impact on the production of DHA and also scoline. So the main conclusion from this was that its forest feedstocks are excellent for the production of PUFA, and we were actually one of the few groups that has actually been using forest resources for DHA production. And we have been able to form a quite good platform for using macroalgae for the production of nutraceuticals. So now turning to the material circle. So here I would like to focus on lignin a little bit. So when we do the organosol pre-treatment and we obtain the solid cellulose fraction, we can also fractionate the lignin and get a solid fraction of lignin. And lignin is normally just burnt, so we have been looking quite a long time to valorize the lignin into materials. And those are two examples of what we are actually doing. So we are looking at the production of lignin nanoparticles. So we can do that by conducting a homogenization step of the mixture of ethanol, water, and lignin. And due to the hydrophilic nature of lignin, we are able to isolate nanoparticles. And why are we interested in lignin nanoparticles? Where there is a big interest in the use of nanoparticles because of their mechanical, thermal stability, antibacterial, and antioxidant properties. And there are several studies using nanoparticles as drug carriers. And they can also be used as supercapacitors for energy storage. And here you can see some pictures of birch and spruce nanoparticles that we have produced here in our lab. This is one example that was recently published, where we isolated lignin from birch and softwood, and we used that to promote the lubrication efficiency of ethylene glycol. And this is just a presentation showing the wear volume of disc lubricated either by only ethylene glycol or by the addition of lignin nanoparticles. And it was shown that actually by adding those lignin particles, we can actually form a very efficient lubricant that actually is only, where the wear volume is only 8.9% of the disc lubricated only by pure ethylene glycol. So this is very interesting to actually promote a renewable alternative for lubrication applications. Then we have also quite many activities within together with the mining industry in Sweden, because there has been a request for them to be able to offer more sustainable processes in the mining industry. And one driving force has been to replace the chemicals that are used in the flotation process. And flotation is the metal enrichment process. And the current use xanthates, they are imported from China, and they are not produced locally. And we try to promote a bio-based economy in Sweden where we can actually produce as much as possible. So the mining industry was very interested in to be able to have a secure supply and have a good quality, and to use a process with a low environmental impact. So in one pre-study, we were able to show that we could use forest residues to produce organosol-based lignin nanoparticles, and that they can be used in the flotation process and replace the xanthate. So this is something that we are currently working on. And we try to develop a flotation process that is more adapted to the use of those lignin nanoparticles. So this project is done together with the Boliden, which is a big mining industry, not only in Sweden, but also globally. And Sveaskog, which is one of the biggest forest companies in Sweden, and Neurone, which is a chemical company. And based on the results, where we could show that those lignin nanoparticles were actually very efficient as flotation collectors, we have just recently been granted a big EU project where we look at the use of these nanoparticles to be used in the flotation process, so that we can recover valuable base metals that are used in the battery industry. So this was a very short introduction of some of the activities that we are doing here at Luleå University of Technology. And I would like to acknowledge my colleagues, Dr. Antti Karnauri, Dr. Leonidas Matsakas, Dr. Alok Patel, Katarina Hurosova, Eleni Krigiani, and Professor Paul Christakopoulos, and also Eva Gran Håkansson for doing the assessment of the prebiotic potential. So now I'm open for questions, if there is something you would like to ask.
Okay, thank you very much for the nice presentation, Ulrika. Can you hear me?
Yes.
Can you now switch off your presentation so that you can read the questions posted by the participants?
I do it like that, and then is it stopped now, or?
I'm not sure. I can still see. Yeah. Can you see the question on your screen now?
No. Aha.
Yeah. Okay. This is actually a questions by one of our participants from our FB page. His name is Muhammad Al Mola. I think his question directed to which compounds from your extract from your bioprocessing extract from your biomass can be used to evaluate the prebiotic potential. That's question number one. And what kind of antioxidant were used? Yeah, this was his. Yes, please, Prof.
So first of all, which compounds can be used? We have only decided to study the oligosaccharides that you can obtain from the cellulose fraction. So that limits us to that we only look at the different degrees of polymerization. And we have focused on cellobios, which is a 2-glucose compound. But of course, there is also prebiotic potential if you also go up longer. So you can have like up to 5 glucose units. So, but for us, we focused on assessing the potential of cellobios, but longer oligosaccharides is also possible. And then, of course, you have also the possibility to use the hemicellulose fraction, which I didn't discuss here, because from the hemicellulose fraction, you could also use XOS, so that this is silooligosaccharides. They have also prebiotic potential. So there are several options, but we in this study only focused on the prebiotics that we can obtain from cellulose. And at this stage, we didn't use any antioxidant.
So I think to put that into the perspective here, in Malaysia, we do have lots of forests, but most of the studies on biomass are focused on different types of source. So we have a lot of oil palm biomass generated in Malaysia. Okay, so the study basically focusing on also like what you're doing here in Sweden. So what do you think on the potential of applying similar information or inputs that you got from your study in your lab using different types of biomass such as that available in Malaysia? What the potentials like?
I think, I mean, so we mainly work with hardwood and softwood, and I guess in Malaysia it would be mainly hardwood that you have.
Yeah, hardwood. Yeah.
Mm-hmm. And what we can see, the prebiotic is much easier to handle, and they also have a higher effect on the probiotic strains that we use. I would say that, I mean, what we have done here could be done exactly the same in Malaysia, because our focus has been to work on the pre-treatment and fractionation, because in this part, for producing the prebiotics, it's very important that you have a pure cellulose fraction. And if you use normally or conventional pre-treatment process, you will always have a fraction of lignin that is recondensed on the cellulose.
Yeah.
And that gives you problem when you are doing the enzymatic depolymerization. And the method that we have developed here is actually the separation of cellulose and lignin actually happens at high temperatures. And that keeps lignin solubilized all the time, so it doesn't recondense on the cellulose. You could see still on the compositional analysis that I showed that we have some lignin in the cellulose fraction, but it's minor. So I think that is very important to have an efficient method to obtain the pure cellulose. But then, I mean, it is the same. And also, the question before about the antioxidant, we also have the lignin that is a very good source for antioxidants. So that's what we think is very interesting in this field when you look at the possibility to produce nutraceuticals from forest biomass. And I don't know how it is in Malaysia, but we work mainly with forest residues. So those studies has been conducting using sawdust, for example. So we get the excess of sawdust that is not used. So this is to actually establish a value chain for sawdust.
Yeah. I'm not sure about the exploitation of sawdust for the production of like the one that you mentioned, but we have different types of application of sawdust here. It's just that I'm seeing that in UTM also we have different groups that are working with biomass, and some uses different kind of approach. Some use thermochemical approach, as pre-treatment. Some uses biological approach. And they are also working, gearing themselves toward using the products from the process. Yes, also for nutraceuticals, and I'm seeing also that there's a potential to go into the nano material part as you presented just now, which is very interesting actually. So one kind of application that we are using here is to use directly as binder. Yeah.
Mm.
So I'm not sure whether you also look into that application as well in your laboratory.
No, not actually. And I, I just like to mention also, now we talked about forest biomass, but of course this process that we are using is agnostic. That means that it can also be used for agricultural residues. I mean, it
Yeah.
can be used for rice straw. It can be used to isolate the lignin from rice straw and then produce nanoparticles from rice straw. And it can be used to isolate the cellulose fraction from agriculture residues.
Yeah, that's great to know, because I know also a group. If I have to refer to in this university UTM, we have group working with rice straw, different types of biomasses. Yeah, so we have one question here again from the our FB page from Mr. Hilman Sharif. So the question is, what do you think about valorization in Malaysia? I think it's more or less similar like what I was asking you just now. The opportunities and etc. Is it like totally different from your country? So you're open to answer it again, Ulrika, or how, please?
I would say like this, from a research perspective, it is actually the same in Malaysia as in Sweden, because we're working with the same kind of feedstock. We are working with forest, we are working with agriculture, and so on. So the methods and the possibilities is exactly equal. But then I think the next, not question, but I think the issue is actually the support from the industry.
Yeah.
How interested are they? And I would say that it's not always very easy here in Sweden, because as you saw in the beginning of my presentation, the pulp and paper industry is very, very big. And I mean, working in collaboration with them, that means that you get quite complicated side streams to work with. So I think that is it is actually the challenge. I mean, who to collaborate with? What is the
Yeah.
industrial interest? And I think for you, for example, I mean, like valorization of residues from rice cultivation, I think that is excellent, because there you can bring a high value into the side streams that are not used at the moment. And that is also the same in Sweden, but I mean, we don't have rice here. We are not so high producer of straws.
So I'm not sure yeah, how is it in Sweden, but for example, in Malaysia, when you talk about let's say palm oil, we have this national board called Malaysian Palm Oil Board, MPOB. So it's for us researchers in the research institute or higher learning institutions. So some of us would get direct feed from them. Yeah. So what are the current nations focus, because they are the right body which is responsible for the development of oil palm in Malaysia. Yeah. So we have such a body in Malaysia. So they would either grant us access to their plantation and get some samples, yes, maybe some current knowledge in the area, or we can also tap some to their contacts. Yeah, that's how we can get the support from the industry or the government agencies. So is it the same in Sweden? Maybe you have similar agency or body or something?
Yes, we have And now a rather big platform in Sweden is called Bioinnovation. So Bioinnovation is to promote research and industrial implementation, and so you get funding from the program, but you also need to put in kind from the companies or cash. So that is like you need to get at least 50% from the companies, and then you can get the other 50% from the program. So
Well, that's a big sum to contribute 50%. Yeah.
Yes, so I mean that is the thing that is quite complicated, and that's why I wanted to stress that I think that the conditions are good when it comes to research, but then I mean we are also very dependent on the need of the industry and the interest of the industry.
Yeah, I also noticed just now in your one of your slides, you mentioned that one of your studies you managed to publish one patent to get it granted, one patent. So to get a patent granted, does it has to involve industry, or you can go alone as a university?
We can go alone as a university. That depends on the contribution of the industry. If they if they did suggested experiments and approaches and so on, then they are also part of the patent. But if we only receive material and we do the thinking in the lab, then we own the patent, or we can patent our research. But that patent that was mentioned was acted together with Boliden, so that is with the company.
Yeah. So I think it's more or less the same everywhere, yeah, because the same practice is also being practiced here in Malaysia. Ulrika, now we have 3 minutes remaining of the session. So do we have any more questions? Maybe the secretariat, do we have any more questions from the FB page? If not, maybe I can, maybe I can pass the session back to our distinguished dean, Professor Rafi.
Thank you, Prof. Zainul, for chairing the session, and thank you to Prof. Ulrika Rova, all the way from Sweden. To be honest with you, Ulrika, I've never been to Sweden, but after listening to your lecture, I think I should pay Sweden a visit. And then perhaps after this COVID-19 ends, I will bring over Zainul to Sweden. Zainul, have you been to Sweden?
Not yet, bro.
All right, okay. Then let's go together and visit Ulrika, yeah?
Yes, I put it on my invitation list.
Excellent. Okay, again, thank you so much, Ulrika. Thank you, Zainul, for chairing the session. And to all our viewers worldwide, thank you for watching our distinguished lecture series. Until next time, I guess, bye for now. Bye-bye.
Bye-bye. Thank you.
Thank you very much, everyone. Bye-bye.